For 3,000 years, Mongolian nomads have lived comfortably through winter conditions where outdoor temperatures reach 40 degrees below zero Fahrenheit with brutal winds that amplify the cold further. Their shelter, called a jijur, known more widely by the Turkish word yurt, maintains interior temperatures comfortable enough for daily life, cooking, sleeping, and raising children through winters that would kill unprotected humans within hours. The structure achieves this performance despite weighing only 500 to 700 pounds, assembling in 2 to 3 hours, using materials that nomadic families can carry on horse caravans, and costing a fraction of permanent construction. The engineering principles underlying traditional yurts combine insights about insulation, thermal mass, shape efficiency, ventilation control, and heating integration that modern prefabricated shelters struggle to match even with contemporary materials and techniques. Understanding how yurts actually work reveals sophisticated integration of simple elements producing extraordinary performance, with implications for anyone interested in efficient shelter, whether for permanent homes, seasonal use, emergency preparedness, or off-grid living. Contemporary applications of yurt principles serve diverse purposes across America, from permanent residences to hunting cabins to glamping accommodations, with the performance characteristics that challenge conventional assumptions about what makes effective shelter. The basic yurt structure consists of a circular lattice wall frame, a center pole-supported roof with radiating roof poles called uni, a center crown ring called a tuno, and covering materials that traditionally include multiple layers of felt made from sheep wool. The circular shape minimizes surface area relative to interior volume, reducing heat losses compared to rectangular structures of the equivalent floor area. The lattice wall folds compact for transport and expands to form structural walls during assembly. The roof pole arrangement distributes loads through the crown ring to the wall frame efficiently, enabling the structure to support heavy snow loads common in Mongolian winter conditions. The felt covering provides the insulation that makes yurts thermally effective. Traditional wool felt produced from matted sheep, wool achieves R values of approximately 2 per inch, with multiple layers producing combined insulation performance that substantially exceeds what the individual materials suggest. A traditional Mongolian winter yurt uses 3 to 5 layers of felt, producing combined R values of 12 to 20 equivalent to modern insulation in permanent construction. The felt also provides substantial air sealing when properly installed, reducing convective heat losses that simple fabric coverings would permit. Batbayar Tsogbayar, a Mongolian architect who has extensively documented traditional yurt construction and performance, has conducted thermal monitoring at herder camps across Mongolia's central regions. His measurements show interior temperatures of 50 to 65 degrees, maintained inside traditional yurts when outdoor temperatures range from -30 to -40 degrees Fahrenheit. The interior heating source is typically a small stove burning dry dung, wood, or coal that produces modest heat output. The efficiency of the yurt envelope allows this modest heat source to maintain habitable conditions that would require massive heating capacity in less efficient structures. The ventilation control provided by the crown ring at the yurt center allows precise management of air exchange. The opening vents combustion products from the interior stove while providing fresh air intake through controlled paths. The sizing of this opening affects both heat losses and indoor air quality, with traditional construction using adjustable covers that allow closure during sleep periods and opening during active cooking hours. The integration of heating, ventilation, and structure through the crown ring represents sophisticated engineering that addresses multiple functional requirements through coordinated design. The shape efficiency of circular construction compared to rectangular construction produces substantial performance benefits. A circular structure enclosing 3/4 square feet of floor area has 63 feet of perimeter wall, while a square structure of equivalent floor area requires 71 feet of perimeter wall. The circular structure has 11% less wall area to insulate, reducing both material requirements and heat loss surfaces. The benefits compound when considering that wind pressure distributes evenly around circular structures rather than concentrating on flat surfaces of rectangular construction, reducing air infiltration that would otherwise compromise insulation performance. The historical evolution of yurt construction spans cultures across Central Asia, with related structures documented throughout Mongolia, Kazakhstan, Kyrgyzstan, and surrounding regions. The specific Mongolian GR represents one variant within a broader family of portable shelter traditions that developed independently or through cultural exchange across steppe cultures. The consistent emergence of similar structural approaches across geographically dispersed cultures confirms the fundamental effectiveness of the underlying design principles rather than representing cultural imitation of single origins. Sarul Erdena, a Mongolian anthropologist who has studied herder communities extensively, has documented how yurt design reflects deep integration with nomadic lifestyle requirements. The structures assemble and disassemble quickly to accommodate seasonal migration patterns. The materials handle repeated assembly and disassembly without significant damage. The furnishings match the circular layout through traditional arrangements optimized for thermal and functional performance. The cultural integration of yurt living with all aspects of daily life produces coherent lifestyles that modern compartmentalized living rarely approaches. The cultural dimensions aren't incidental decorations, but integral aspects of how yurt living works across all its practical requirements. The contemporary applications of yurt principles in Western contexts have developed rapidly across recent decades. Manufactured yurts produced by several American companies serve markets ranging from permanent residences to recreational applications to commercial hospitality operations. These contemporary yurts typically incorporate modern materials, including engineered fabrics, synthetic insulation, and structural engineering designed for specific climate conditions while retaining the essential design principles that make traditional yurts effective. The American yurt market has grown substantially, with several manufacturers producing thousands of units annually for diverse applications. Trevor McKenzie, a manufactured yurt installer based in Oregon who has erected over 200 contemporary yurts for American clients, has documented typical performance characteristics across his installations. The modern yurts he installs maintain interior temperatures of 60 to 72 degrees during winter conditions, with outdoor temperatures ranging from 15 to 30 degrees through modest heating equipment, including wood stoves, propane heaters, or electric heat pumps. The smaller heating loads compared to conventional construction enable efficient operation from modest equipment, matching the traditional Mongolian approach of using small heat sources effectively. The insulation options for contemporary yurts include various approaches beyond traditional felt. Fiberglass insulation provides cost-effective thermal performance when properly installed. Wool felt insulation continues providing traditional performance at premium cost. Bubble reflective insulation offers unique characteristics combining modest R values with radiant reflection. Rigid foam panels provide maximum thermal performance at highest cost. The insulation selection affects both thermal performance and cost, with options suited to different applications, climates, and budgets. The cost comparison between yurt construction and conventional construction varies with specific applications, but typically shows substantial advantages for yurt approaches. A 30-foot diameter manufactured yurt with insulation, windows, and basic utilities costs $10,000 to $18,000 installed. Equivalent floor area, conventional construction costs $60,000 to $120,000 depending on location and specifications. The Yurt approach provides 70 to 85% cost savings while delivering satisfactory living environments for appropriate applications. The dramatic cost advantage makes yurts attractive for situations where conventional construction economics don't work. The seasonal and climate considerations affect yurt application success substantially. Yurts perform excellently in climates with moderate to cold winters where their insulation and wind resistance characteristics provide value. Hot, humid climates produce more challenging conditions as yurt envelopes don't breathe moisture as effectively as conventional construction. Very wet climates require attention to roof drainage and moisture management to prevent fabric deterioration. Matching yurt application to appropriate climate conditions produces satisfactory outcomes while avoiding climates where the approach struggles to provide needed performance. Now for the obstacles and limitations that affect yurt applications in American contexts. First, the permitting challenges vary substantially across different jurisdictions. Some American counties and municipalities have developed specific yurt permitting categories with reasonable requirements matching the structure type. Other jurisdictions apply conventional building code requirements that create substantial obstacles for yurt construction. Some locations essentially prohibit yurts through requirements incompatible with their construction characteristics. Investigating permitting requirements in specific locations before committing to yurt plans prevents frustration from discovering incompatible requirements after planning and purchase. Second, the insulation and weatherization limitations create comfort challenges in extreme climates or demanding applications. Standard manufactured yurts provide thermal performance adequate for seasonal use and mild climates, but may struggle in severely cold climates or extended winter use. Upgraded insulation packages improve performance but increase costs toward conventional construction levels. The fundamental limitations of fabric envelope construction cannot match performance of solid wall construction regardless of insulation investment, limiting applications in the most demanding climate conditions. Third, the financing considerations for yurt purchases sometimes prove challenging. Conventional mortgage lenders decline to finance yurt purchases, limiting buyer options to personal loans, cash purchases, or specialized lenders. Insurance coverage for yurts varies by insurer, with some providing standard coverage and others declining or charging premium rates. The financial infrastructure for yurt ownership lags conventional construction, creating practical obstacles even when local permitting permits the construction type. Fourth, the security characteristics of fabric-walled construction differ substantially from solid wall construction. Fabric walls provide minimal resistance to determined intrusion, limiting yurt suitability for applications requiring security against theft or intrusion. The sound transmission characteristics allow conversation audibility across fabric walls, limiting privacy compared to solid construction. These characteristics suit yurts to remote, low-density applications rather than urban or suburban settings where security and privacy considerations dominate. Fifth, the durability considerations affect long-term economics of yurt ownership. Quality fabric covers typically last 10 to 20 years before replacement, representing ongoing cost that conventional construction doesn't impose. Structural components including frames and crown rings can last 30 to 50 years with appropriate care. The replacement cycle costs must be factored into long-term ownership economics, though, typically remain favorable compared to conventional construction maintenance and replacement cycles. Despite these considerations, yurts offer proven performance for appropriate applications at costs dramatically below conventional alternatives. The combination of efficient thermal performance, rapid construction, portability, and cultural connection to proven traditional approaches appeals to diverse American users seeking alternatives to conventional construction. The integration with passive solar principles produces enhanced performance for yurts in appropriate climates. South-facing windows capture winter solar gain that supplements heating from mechanical sources. Thermal mass elements, including stone or water, features absorb solar energy for release during cold periods. Proper orientation and window placement can capture substantial percentages of heating requirements from passive solar in appropriate locations. The integration of traditional yurt construction with contemporary passive solar design produces hybrid approaches that leverage benefits from both traditions. Anya Demkova, a Russian-American architect specializing in portable shelter design, has conducted comparative performance analysis between yurts, conventional construction, and other alternative shelter approaches in cold climate applications. Her analysis shows yurts providing optimal value for applications where portability, rapid construction, or low cost matter significantly. Conventional construction proves superior for permanent installations where maximum performance and minimum maintenance matter most. Other alternative approaches, including small prefab cabins, container construction, and various specialized shelter types, offer different trade-off patterns suited to specific applications. The comparative analysis clarifies where yurts excel and where other approaches might serve better. The environmental implications of yurt construction generally prove favorable compared to conventional construction. The embodied energy in manufacturing yurt materials, including fabrics, insulation, and structural components, runs substantially below that of conventional construction. The operational energy for heating smaller structures with efficient thermal envelopes remains modest. The lack of foundation for most yurt installations eliminates substantial environmental impacts associated with conventional construction. The combined environmental footprint of yurt dwelling typically compares favorably with any alternative structure of equivalent living area. The portability benefits of yurt construction enable applications that permanent construction cannot address. Families wanting seasonal dwelling in remote locations can erect yurts temporarily without permanent site development. Hunting, fishing, and wilderness experiences can use yurt accommodations at sites where conventional construction would prove impractical. Emergency and disaster response applications can deploy yurts rapidly to provide shelter for displaced populations. Educational programs can use yurts to teach traditional skills and demonstrate alternative living approaches. The diverse applications showcase the flexibility that portability provides. The cultural dimensions of yurt living extend beyond pure functional shelter characteristics. The circular interior space creates different spatial relationships than rectangular rooms produce. The focal heat source, typically centered in traditional yurts, creates gathering points that shape social interaction. The connection to nomadic traditions spanning millennia provides cultural depth that contemporary construction rarely offers. Families choosing yurt living often appreciate these qualitative dimensions alongside the practical and economic considerations that drive their decisions. The structural engineering of contemporary yurts has evolved substantially, from traditional designs to accommodate specific American building requirements. Wind load engineering addresses the severe conditions that can affect circular structures during storms. Snow load engineering ensures that roof structures can support the weight of accumulated winter snow in northern climates. Seismic engineering addresses earthquake zones where rigid structures face specific vulnerabilities. The engineered structural systems in contemporary yurts typically exceed the loads that traditional construction was designed to accommodate, providing safety margins appropriate for American permitting and insurance requirements. The utility integration for yurt installations enables comfortable living with modern conveniences. Electrical systems including appropriate wiring, outlets, and lighting function identically in yurts compared to conventional construction. Plumbing systems for water and drainage can be installed in yurts used as permanent residences, though the structural flexibility requires specific attention to pipe routing and support. Internet and telecommunication services function normally through wireless approaches that don't require envelope penetrations. The utility infrastructure can make yurt living essentially equivalent to conventional residential comfort for applications where this matters. The foundation options for yurt installations provide flexibility matching different application requirements. Simple gravel pad foundations suit seasonal or temporary installations. Wooden deck foundations elevated above ground level provide stability and protection from ground moisture for extended use. Permanent concrete foundations serve applications where maximum durability and stability matter. The foundation approach affects cost, permitting requirements, and performance characteristics. Selecting appropriate foundation approaches for specific applications produces outcomes matching user needs without unnecessary expense. Helen Bartholomew, a permaculture designer in Washington State who has integrated yurts into sustainable homestead designs for over a dozen clients, has documented how yurts function as elements within broader property development strategies. Her projects typically combine yurts with outdoor cooking areas, garden infrastructure, workshop spaces, and related improvements that collectively create full homestead functionality. The yurts serve as primary residential spaces, while other facilities handle specialized functions that yurts accommodate less efficiently. This integrated approach maximizes the value that yurts provide while working around their specific limitations. The winter heating approaches that work effectively in yurts require specific consideration. Small wood stoves, sized appropriately for yurt interior volumes, produce adequate heating while avoiding overheating that oversized stoves would cause. Propane heaters provide clean burning heat with automatic controls at the cost of fuel expense during extended heating seasons. Electric heating options, including space heaters or small heat pumps, work for yurts with electrical service connections. The heat source selection affects operating costs, convenience, and environmental considerations, with different options suiting different application priorities and site conditions. The ventilation management during heating season balances air quality concerns with heat retention. Traditional yurts use adjustable crown rings to modulate ventilation throughout the day, matching cooking, sleeping, and active occupation patterns. Contemporary yurts typically use similar crown rings with improved sealing capabilities. Mechanical ventilation with heat recovery can provide superior performance in colder climates, or for health-sensitive occupants, though adds complexity and cost that traditional approaches avoid. The ventilation approach interacts with heating approach to affect overall performance outcomes. The cooling considerations for summer use in yurts involve different principles than heating season operations. Natural ventilation through crown rings and wall openings provides substantial summer cooling when outdoor temperatures moderate. Reflective exterior covers can reduce solar heat gain during hot summer periods. Shade structures around yurts provide additional cooling through reduced solar exposure. The combination of ventilation, reflection, and shading typically enables comfortable summer occupancy in climates where summer temperatures remain moderate. Very hot climates may require active cooling equipment that compromises some yurt principles while enabling habitable conditions. Nina Prescott, a yurt manufacturer sales representative who has helped hundreds of customers select appropriate yurt configurations for their specific applications, has documented common patterns in customer priorities and ultimate satisfaction. Her experience shows that customers who carefully match their yurt selection to their specific application priorities and site conditions report high satisfaction across diverse use cases. Customers who select based primarily on aesthetic considerations without sufficient attention to practical requirements sometimes experience disappointment when performance characteristics don't match their needs. The pattern suggests That thoughtful matching of yurt characteristics to specific application requirements produces the best outcomes. The assembly process for contemporary yurts typically requires a team of 2 to 4 people working for 4 to 8 hours, depending on yurt size and optional features. The process proceeds in defined sequences, starting with platform preparation, continuing through frame assembly, progressing to cover installation, and concluding with interior finish work. Most manufacturers provide detailed instructions, video tutorials, and telephone support that enables successful self-assembly by motivated owners. Professional assembly services exist in regions with substantial yurt activity, though the cost savings of self-assembly often appeal to yurt buyers who are already seeking affordable alternatives to conventional construction. The long-term ownership patterns for yurt dwellers reveal interesting lifestyle trajectories. Some families begin yurt living as temporary accommodations during property development for conventional construction and discover they prefer yurt lifestyle indefinitely. Others purchase yurts for recreational use and gradually expand use toward primary residency. Some buyers select yurts specifically as long-term primary residences from initial purchase. The diverse ownership trajectories suggest that yurt living works well for many families beyond its initial positioning for specific applications. The flexibility to adapt yurt applications as family circumstances evolve provides value that more rigid housing approaches cannot match. Consider what yurt dwelling means for Americans exploring alternatives to conventional construction. The option to establish a warm, functional home for $10,000 to $20,000 rather than $100,000 to $300,000 transforms housing accessibility for some families. The ability to assemble and disassemble enables lifestyles that permanent construction precludes. The thermal performance adequate for comfortable year-round living in appropriate climates enables genuine habitation rather than just recreational use. The cultural connection to 3,000 years of nomadic tradition adds meaning beyond pure shelter function. The environmental footprint remains modest across the ownership lifecycle. The rapid construction allows housing establishment in timeframes that conventional construction cannot match. The opportunity exists for families willing to consider shelter approaches different from conventional American norms. The evidence supports the performance across Mongolian winter extremes and diverse American application contexts. The knowledge and manufacturing infrastructure support practical implementation. The costs remain dramatically below alternatives. The obstacles are real but manageable for appropriate applications. The choice to pursue yurt living or dismiss the option entirely depends on specific circumstances, priorities, and locations. The ancient Mongolian engineering offers lessons and practical options that deserve consideration alongside conventional construction approaches. For the right family in the right situation, yurt dwelling represents genuine alternative that modern American culture rarely considers despite compelling advantages in appropriate contexts.